Hi everyone, I'm Ben. Welcome back to my YouTube channel. In previous video, we covered the lead-driven cavity example. And so today, we will dive into part 3 of NVIDIA Modulus series. Focusing on turbulence basic and the lead-row equation turbulence model. We will implement this turbulent model in the lead-driven cavity simulation. Walk through the code and visualize the result and compare them with OpenFOAM. And everything, the code or the results you can check in this GitHub website. In part 1, we will integrate the zero equation turbulence model into a lead-driven cavity example. Previously, the lead-driven cavity had the Reynolds number of 10, but now we have increased it to 1000 and making the flow more turbulent. The model uses effective viscosity in the Navier-Stokes equation calculated from the mean strain rate tensor to simulate this turbulence flow. So what is effective viscosity? It is essentially a modification of the Navier-Stokes equation, replacing mu with mu effective. So this adjustment allows for a more computationally efficient and accurate simulation of turbulence in practical engineer application. So understanding effective viscosity in the linear equation turbulence model is key. Unlike model like K epsilon or K omega, which requires solving additional transport equation, this model directly estimates turbulence viscosity using local velocity gradient and wall distance. This equation includes the missing length and strain rate magnitude to account for a turbulence effect. The missing length is determined by the normal distance to the nearest wall and calculated using the SDF function in the NVIDIA Modulus. It is defined as the minimum between this normal distance and maximum reference distance in the flow field. So since the missing length influence effective viscosity, being farther from the wall generally result in a higher value. And also, the magnitude G effectively capture the amount of sharing in the flow. If the velocity gradient are large, and G will increase, and leading to higher turbulence. So we have the molecular viscosity mu and the turbulence viscosity mu t. And the effective viscosity is the sum of the molecular viscosity and the turbulent viscosity. So this modification replaces mu in the Navier-Stokes equation to account for turbulence effect. So mu is changed to mu effective. So that is all. And the advantage of the linear equation model is that it does not require additional transport equation, unlike K epsilon or K omega. It is computationally fast and relies only on algebraic calculation, making it suitable for real-time simulation. It also works well for simple flow case. Also, while the linear equation model offers speed and efficiency, it lacks the accuracy to capture complex turbulence effects such as separation or wakes. And so how NVIDIA modules use the linear equation model. At a high level, you only need to import the package in Modulus, then use the linear equation function and by inputting the new maximum distance and dimension and time, it will automatically compute the mixing length and the strain rate. So it's import from here. And also, if you want to dive into more deeper or check the more detail, you can check this website in visual equation knowledge. And once we finish implement the zero equation model and integrate into the Navier-Stokes equation using the effective viscosity, the approach remains the same as in the previous case and part 2 lead-driven cavity example case. We simply need to learn how to import the linear equation model into the system, and then we can follow the same process as before. In part 2, we will go through the code walkthrough. This part is very similar to the previous video on the lead-driven cavity example. We still need the geometry and governing equation. However, in this part, we introduce a new equation, a linear equation model to modify the viscosity for the effective viscosity calculation. We need to include the linear equation model package, which is a new addition in this part. And we also define the same geometry as in the lead-driven cavity example. And we also add the turbulence model. Introducing the turbulence model, we then incorporate this linear equation model into the Navier-Stokes equation and replacing the nu with E to compute the effective viscosity nu effective. We also need to set the boundary condition, the top wall move with the constant velocity of u equals to 1.5. And this is a slight difference from the previous example, where u is equal to 1. In this case, u is 1.5. And the interior constraint, however, remain the same, so you can follow the same rule as before. The result will be compared against OpenFOAM data, which is provided by NVIDIA. They have made this result available on their website, where you can download all the data including NVIDIA Modulus example and supplemental material. In part 3, I will show you how to visualize the output result using TensorBoard and Jupyter Notebook. And I will also provide the code on my GitHub so you can download it and follow along with my step. Part 3 here. So in the first step, we need to download the NVIDIA's Modulus Sync example results in this website. So download. And the next step is we need to open our Modulus Jupyter Notebook in Docker. and we need to upload our example scene. We just download from the NVIDIA modules resource, upload, and we create a new notebook. Rename this. And finish. So we will have the example scene. And so we will have LTC and OpenFOAM, and every OpenFOAM simulation result is in here. And you can copy these three into the our modular scene example LTC OpenFOAM, and you can copy to here. Thing is, you can go to my website and here and download this too. And put it into here, and I just modify this example code to this picture, add some picture. So I using the custom validator plotter to plot our output result in the TensorBoard. So we just can visualize the P and U V new, and we extract the P true means the OpenFOAM result, and the pre-predict is mean NVIDIA modules result, and we using P true minus P predict, so we can compute the difference. And also I set up the color bar limit, which is here, color bar limit. I just follow the same rules in the NVIDIA modules documentation, this one. So I just follow this color limit. So yes, everything I'm done in this code, and using the data and CMap jet, which is more like this rainbow color, and the extent is the cavity domain. And also I revise the code in here, validator. In the sample code they using the validator plotter, but now we using this custom validator plotter. And also the output, we need to have the U, V, new, and P. Yes, this is all I revised in the example code. So let's run this. So I create this notebook, and I just can run it. and using the TensorBoard run, and we can check on this. So in the TensorBoard, you can click this image. Yes, so we will have our Modulus output result and the open form, and also the difference. And you can use this toolbar. Yes. Yes, so you can see the U is more, it will be more likely the open form result. Yeah. So in summary, in this video we define the differential equation turbulence model in Modulus sim, and we set up the lead-driven cavity flow problem with Reynolds number equals to 1000. And we also implement the boundary condition and domain constraint and validation, and we run the solver and compare with open form result. And I also find the NVIDIA Modulus thing results in that website, and it has a huge of result in this documentation. And I think that is all for this video, and I hope you learned something in this video. Thank you for your watching.